Okay, imagine this. The universe ending, right? But what if that end wasn't practically infinite years away? What if it was actually much, much sooner than we ever thought?
Yeah, it's quite a startling idea.
We're going to unpack this because there's some really groundbreaking research out, and it kind of throws a curveball at how we've understood the universe's lifespan. And since you're here to get smart fast, well, this deep dive is definitely for you.
It's a huge shift, really. For ages, the estimate was, almost unbelievably long, like 10 to the power of 1100 years, just mind-boggling.
Right.
But this new study, it's from researchers over at Radboud University in the Netherlands, published in the Journal of Cosmology and Astroparticle Physics. Let's just call it IDR for short.
Okay, IBR.
Yeah, they've revised that estimate way down. We're talking around 10 to the power of 78 years now.
Wow, 10 to the 78. That's still enormous, but compared to 10 to the 1100.
Exactly. It's like comparing an atom to the entire known universe. That's the kind of scale difference we're dealing with. It's a massive recalculation.
Absolutely staggering. So the big question is how? How did they arrive at this, drastically shorter timeline? What were we missing?
That's what we need to figure out.
Right. So our mission today is basically to understand this cosmic recalculation, what it means, and just to be clear right up front, don't panic. This doesn't change your weekend plans.
Not at all. We're still talking vast, vast amounts of time.
We'll dig into Hawking radiation, the role of white dwarfs, which is kind of the surprise element here, and even touch on dark energy. Get you the full picture.
Sounds good. So let's start with Hawking radiation. It's a concept that's been around since the 70s, thanks to Stephen Hawking.
Right, the idea that black holes aren't perfectly black.
Precisely. He theorized that they actually emit a tiny bit of radiation, and over incredibly long timescales, this makes them lose mass and, well, eventually just evaporate.
Okay, and that slow evaporation, especially for the biggest black holes, that was the basis for the old super long estimate, the 10 to the 1100 years.
Exactly. That was seen as the ultimate endgame, this incredibly slow fade-out, the ultimate cosmic slow burn.
But the IDR research, they took Hawking's theory and looked somewhere else.
Yes, that's the key. They didn't just focus on black holes. The team, folks like Heino Felk and Walter von Zwijlacum, they turned their attention to another type of really dense object. White dwarfs.
White dwarfs. Okay, those are the leftovers from stars like our sun, right, after they burn out.
That's them. They're the collapsed cores. Incredibly dense. Think of squeezing a whole lot of stuff into a tiny space. And they stick around for a very, very long time themselves.
So how does Hawking radiation apply to them? They're not black holes.
Well, this is where it gets interesting. The researchers figured that Hawking's theory isn't just about black holes, it's linked to extreme density and the curvature of spacetime it causes. They applied the core idea to white dwarfs.
Ah, okay. Because white dwarfs are also incredibly dense.
Extremely dense. And what they found, theoretically, is that the density of any object like this is crucial for how quickly it would dissolve or evaporate via this Hawking radiation mechanism.
So it's not just black holes slowly evaporating, but potentially white dwarfs too?
Exactly. Black holes evaporate incredibly slowly, partly because of their huge size. White dwarfs, being super dense but much smaller, would also evaporate through this process, but on a different timescale.
A faster timescale.
Significantly faster than the supermassive black holes, yes. Still unbelievably long by human standards, but much, much shorter in the grand cosmic scheme.
And that's the crux of it. Factoring in the evaporation of white dwarfs gives us this new, shorter deadline for the universe.
That seems to be the main finding. By considering the eventual end of these very stable, very dense white dwarfs, they identified a new theoretical limit for how long matter itself can persist.
So the universe can't last longer than its most durable, dense components, basically.
That's the idea. As one of the authors, Heino Felke, put it, the final end of the universe is coming much sooner than expected. It sets this new horizon.
Which leads to that 10 to the 78 years estimate.
Precisely. It's still an almost unimaginable length of time, but it's a dramatic shift in our understanding.
Okay, let's address the elephant in the room, or maybe the planet in the room. What about Earth? Does sooner than expected mean anything for us, like personally?
Right. That's really important to clarify. No, absolutely not. This new timeline, even though it's shorter cosmically, has zero bearing on the immediate future of Earth or our solar system.
Our local forecast is unchanged.
Completely unchanged. We still expect, based on current science, that in about 1 billion years, the sun will get too hot for liquid water on Earth.
And then eventually it expands.
Yep. In maybe 8 billion years or so, the sun becomes a red giant and will likely swallow Earth whole.
So long before any white dwarfs start evaporating in a significant way.
Oh, long, long before. The IDR study itself makes a point of saying, humankind needn't worry too much about the end of the universe. That 10 to the 78 years is still just vast. Our star system will be ancient history by then.
Okay, good to know. Now, this revised end date comes at an interesting time, doesn't it? Because there's also stuff happening with our understanding of dark energy.
Indeed. It's another piece of the cosmic puzzle that seems to be shifting a bit. Dark energy, that mysterious force we think is making the universe expand faster and faster.
Yeah. What about it?
Well, some recent findings, even from earlier this year, have hinted that dark energy might not be constant. It might actually be weakening over cosmic time.
Weakening. Okay, wait. If the force pushing everything apart is getting weaker, what happens then?
That opens up some pretty wild possibilities. If the expansion isn't accelerating forever, then maybe, just maybe, gravity could eventually win out again.
You mean pull everything back together?
Potentially. It could lead to the universe eventually stopping its expansion and collapsing back in on itself, the so-called Big Crunch.
Whoa. A big crunch instead of a slow fade out or evaporation. That's a very different ending.
It is, and it really highlights how much we're still learning. Mustafa Ishaq Bashaki, a cosmologist commenting on this, posed the question of whether such an end would be good or bad. It's certainly thought-provoking.
So we have these two lines of inquiry sort of converging, one suggesting a shorter lifespan based on matter evaporating, the other questioning if the expansion driving everything apart will even continue forever.
Exactly. Both point towards a potentially more dynamic, maybe more complex, long-term future for the cosmos than just endless expansion and decay.
It makes you realize how much is still unknown. Are we getting closer to answers with things like new telescopes?
Hopefully. We have instruments like the Euclid Space Telescope and the Vera C. Rubin Observatory coming online or already working. They're specifically designed to map the universe and study dark energy in incredible detail.
So maybe they'll shed more light on whether dark energy is weakening or how this white dwarf evaporation fits in.
That's the goal. They promise to give us much deeper insights. This IDR study adds a really significant new piece to consider in that grand cosmic puzzle, a shorter, though still incredibly distant, end date.
Okay, so let's quickly recap the key takeaway for you listening. New research, the IDR study, suggests the universe might end around 10 to the power of 78 years from now.
Which is much sooner than the old estimate of 10 to the 1100 years.
And this comes from applying Hawking radiation not just to black holes, but also thinking about how other super-dense things like white dwarfs will eventually evaporate too. Their density is the key factor.
And crucially, let's say it again, this timescale, however revised, poses absolutely no immediate threat to us here on Earth. Our sun's evolution is the determining factor for our much, much nearer future.
Right. What strikes me, though, is how these different areas, the fate of matter itself, the behavior of dark energy, are kind of intersecting now. It paints a more complex, maybe more interesting picture of the universe's ultimate fate.
It really does. It reminds us that cosmology is a constantly evolving field. We're always refining the picture.
It definitely makes you think. So here's a question for you to ponder. Considering these immense timescales, even the revised shorter one, and all these cosmic mysteries still out there, what does this new perspective on the universe's end make you think about our place right here, right now?
That's a good one. It certainly puts things in perspective.
And for those of you focused on exams like the UPSC, keeping up with this kind of fundamental cosmological research is actually quite relevant.
Definitely.
Understanding the universe's evolution, concepts like Hawking radiation, dark energy, these are core topics in science and tech, important for mains, maybe even prelims sometimes, as part of your current events awareness.
Absolutely. It's about grasping the big picture of the cosmos and how our understanding of it changes with new discoveries.
So if you found this deep dive thought-provoking, if it sparked some curiosity, please do hit that like button and subscribe for more explorations like this.
And please, share your thoughts or any questions you have in the comments section below. We really value that engagement.
It helps us all understand these complex topics better.
It really does. Dialogue is key.
And just to be crystal clear, the main source we explored today was that study from Radboud University, published in the Journal of Cosmology and Astroparticle Physics, which we've been calling IDR.